Today, we're going to pull back the curtain on one of the true unsung heroes of computing, the compiler. It's this fundamental piece of software that makes pretty much everything we do on our computers even possible. So what in the world is it, and how does it perform all this digital magic?
Well, it all starts with a really basic problem. You've got programmers, right? We write instructions in languages that are designed to make sense to us, to other humans. But our computers, they live on a totally different planet, speaking a completely different language.
Exactly. We're over here writing in languages like C++, Java, or Python, which are full of words and logic that we can follow. The computer's processor, though, it only gets machine code, just a raw stream of ones and zeros. That's it. That's all it speaks. So how on earth do you bridge that massive communication gap?
That's where the compiler steps in. A compiler is this special program that is, for all intents and purposes, a master translator. Its entire job is to take the source code that we wrote and systematically convert it into that binary machine code the processor can actually execute. It is the essential link that turns a human idea into a machine action.
So here's what we're going to cover. First, we'll look at the compiler as this universal translator. Then we're going to peek inside the black box to see how it actually works. After that, we'll explore the different types of compilers out there. And finally, we'll talk about why they're such a critical bridge to our hardware. All right, let's start with the big picture. What is the compiler's most fundamental role? You know, this quote from Nicholas Wirth, who was a giant in the world of programming languages, just nails it. Compilers aren't just some utility. They are the literal foundation that connects the abstract world of software, our ideas, to the physical reality of silicon chips. Without them, high-level programming just wouldn't be a thing. So how does this translation actually happen? I mean, it seems like magic, but it's really a highly structured multi-step process. So let's follow one single line of code on its journey from text all the way down to machine instructions. Okay, this diagram shows the classic phases of compilation. Now, it might look a little complex at first glance, but don't worry, we're going to break it down. Just think of it as an assembly line. Each phase takes the output from the last one, transforms it a bit, and adds more structure and meaning as it goes.
And here's our guinea pig for this journey. It's a simple, straightforward line of code that you'd find in tons of programs. We're about to see exactly how a compiler reads this, makes sense of it, and translates this very human-readable instruction.
We're going to focus on 4 main stops on this journey. First, breaking the code into words, then checking its grammar, then understanding its meaning, and finally, actually generating that optimized output.
The very first step is called lexical analysis. You can think of the compiler acting like a scanner here. It reads our string of characters and groups them into logical chunks called tokens. It gets rid of all the fluff like extra spaces and comments and just focuses on the parts that actually mean something. So our friendly line of code gets transformed into this, a stream of tokens. Position, initial, and rate are all labeled as identifiers. You can just think of them as variables. The compiler keeps track of them in a special list. The equals sign, plus sign, and multiply sign become operator tokens, and 60 becomes a number token. See? The code isn't just a blob of text anymore. It's a structured sequence.
Next up, syntax analysis, or as it's often called, parsing. Now the compiler takes that stream of tokens and checks if they're arranged correctly according to the language's grammar rules. It's basically asking, is this a valid sentence? Just like in English, you can't just throw words anywhere. They have to follow a certain structure. And to figure this out, the parser builds this really cool data structure called an abstract syntax tree, or AST for short. And this is where the compiler has its aha moment. It's no longer looking at a flat line of text, it's building a hierarchical structure that it can actually understand. The equal sign is at the root, and the other operators and variables branch off from there.
And the beauty of this tree is how it makes the order of operations totally explicit. Just look at the structure. You can see that rate times 60 is grouped together under the multiplication node, and the result of that is then fed into the addition node. The compiler now knows, just by looking at the tree's shape, that it has to do the multiplication before the addition.
So this abstract syntax tree becomes the master blueprint for everything else. The next phases use it to check if the blueprint is even logical, like you can't add a number to a word, right? That's semantic analysis. Then, during optimization, it might cleverly rearrange the tree to make it run faster. And finally, in code generation, it walks through this blueprint step by step to produce the final machine instructions. Our little line of code has made it.
Okay, so now that we've seen how a compiler works, let's look at the different strategies they can use. The core job is always translation, but it turns out there's more than one way to get it done.
Yeah, compilers are definitely not a one-size-fits-all kind of tool. They come in all sorts of flavors, and we can categorize them by what they do, when they do it, and what kind of machine they're building for.
First up is the classic distinction, compiler versus interpreter. A traditional compiler, like we've been talking about, translates the entire program at once, creating a super fast standalone file you can run. An interpreter, on the other hand, translates and runs the code one line at a time. It's generally slower, but it can make finding bugs a lot easier while you're developing. We can also categorize them by when they do their work. An ahead-of-time, or AOT compiler, is the classic model. It translates everything before you ever run the program. But then there's the just-in-time, or JIT compiler, which does something really clever. It compiles code while the program is running. And this is a huge advantage because it can see exactly what the program is doing in real time and make super specific optimizations on the fly.
And finally, let's talk about the target. A native compiler creates a program for the exact same kind of machine it's running on, like building a Windows app on a Windows PC. A cross-compiler, though, builds a program for a totally different system. And this is incredibly common today. Think about developers using their laptops to build apps for smartphones, game consoles, or all sorts of tiny embedded devices.
So let's zoom back out and really hammer home why all of this is so incredibly important for, well, everything we do with computers.
Here's the bottom line. Compilers are what make modern software development possible. They let us think and work in powerful, abstract languages without having to memorize the nitty-gritty instruction set of every processor. They work tirelessly behind the scenes to make our software fast, and they make our code portable so we can run it on different kinds of computers. Every app on your phone, every website you visit, the operating system you're using right now, all of it relies on compilers.
And that brings us to a really interesting final thought. Compilers are what allowed us to leap from writing raw machine code to using the powerful languages of today. As they keep getting smarter, using AI and even more advanced tricks, it really makes you wonder, what's next? What will be the next great leap forward in how we tell our machines what we want them to do?